Saxon Advanced Mathematics Lesson 62. A nice straight algebra lesson with two parts. The first part, abstract coefficients, is nothing new and earth-shaking, but it is taking us one step closer to a lesson where we're going to use this calculation. So this will come back to us. Basically, what we're doing here that's a little bit different is we're dealing with abstract coefficients in systems of equations. So let me show you. This is a pattern that we're going to see often. In the future, we will often do this where there are numbers for the A, B, C, and the D, E, and F. John makes the point, which I think is interesting, is that when we use, excuse me, when we create formulas and things where we're using letters to stand for numbers, we use letters from the beginning of the alphabet to stand for numbers, and we use letters at the end of the alphabet to stand for where the variables will be. So in the future, you'll see equations like this, only there will be numbers for the front of the alphabet positions, and we'll still have the X's and Y's for the X's and Y's. Now, what John is asking us to do is to solve this equation for Y. Now, he's never going to ask us to solve it for A, B, C, D, E, or F. He's going to ask us to solve it for X or for Y. So our hint is to eliminate either the X or the Y, depending on what he's asked us for. He asked us to solve for the Y's, so that tells us eliminate the X's. All right, and the way that we'll do that is classic elimination style adjustment, like we've always done. We'll multiply, we want to make these two terms cancel. So we'll multiply the top by D, and we'll multiply the bottom by minus A. And that will cause this to be ADX and this to be minus ADX. They'll drop out. We'll be left with nothing but Y's. It'll all be glorious. All right? So let's multiply. It'll be ADX plus BDY equals CD, right? And then minus ADX. I don't have to say it out loud. You see what I'm doing, right? And then we will add the two together. That's our system of equations. I'll put that there so you see it again. This cancels. We get, oh wait, this is supposed to be, this should be a Y. My bad. I just wrote the wrong letter there, okay? Because it's minus A times EY. So minus AEY equals CD minus AF. Now we're ready to do what we're used to doing. We'll factor out the desired variable. And then we'll divide away the part we don't want. And there's my Y over there. I'm going to write it again over here and box my answer like so, because I don't want to write all this over again. CD minus AF over BD minus AE equals Y. Okay? Now, you may look at this and go, is this really an improvement on this? Not necessarily, but you'll see that there are going to be problems where we want to move from here to here, and this is going to be very helpful to us. So we're practicing doing it now. Later we'll do this same calculation in the context of a problem where that answer helps us. All right, and there's one more of these. And in this one, John is using a crazier looking set of variables just to give us practice with that. He's giving us subscripts. Notice that the last time we went A, B, C, D, E, F. This time we have A, B, C twice, and we have the little subscripts to help us distinguish one from the other. John wants us to solve for X. So we remember our overall strategy that we're never going to eliminate the A, B's, and C's. It's either X or Y is what we're eliminating. This time we want to solve for X, so that tells us we want to eliminate the Y's, right? Simple decision. As soon as we see solve for X, we know we want to eliminate the Y. As soon as we see, let me just flip back here and show you again. As soon as we see this, this tells us we want to eliminate the X's, okay? So, John is very direct in giving us a game plan. All right, so somehow we have to figure out how to make these go away. Well, it's straightforward elimination here. I didn't put this on here, if that bothers me. It's straightforward elimination, so we need to set these up so they'll cancel. So I'm going to multiply this one by B2 and this one by minus B1. I like to put my minus in the lower one because that just feels better to me, but you could put the minus up there too. All right. So now I'm going to multiply. A1, B2, X. It gets kind of crazy, doesn't it? All these, what I'm doing is I'm going in order by letter first and then subscript. Okay. It is a little crazy with the subscripts. I find it much easier to keep track of everything with the A, B, C, D, E, F, but this is doable. Okay, so now we've multiplied everybody through by what we decided they should be multiplied through by. These two do not cancel. It looks for a minute like they do, but if you look carefully at the subscripts, you go, oh no, that's fine. These are the ones that cancel. So we get A1, B2X minus okay, that looks good. There are our X's. We factor them out. And we get A1B2 minus A2B1. That's enough to make you go crazy, isn't it? It's all a bit crazy. But we just keep following the steps. Now we're going to divide by A1B2. And this is my answer. I'm going to just do this and then write equals X. And let me check. B2C1 minus B1C2, A1B2 minus A2B1. Yay, that's our correct answer. All right, so it's really just elimination as we learned it years ago, Algebra 1. It's remembering that if we're asked to solve for X, that means eliminate the Y's. If we're asked to solve for Y's, it means eliminate the X's. We choose carefully to set up the elimination, and we don't let the wacky subscripts make us crazy. Or at least we try. Okay, that's all I have to say about that topic. Like I said, we're going to use that in a future calculation, so pause your brain on that topic. The second piece of this lesson is called linear variation. Now, you know how it was a lot in Algebra 2. We pretended we were scientists and we had the lab books and we had the graphs and they had the dots in them, the results of the different. It would go like this. This was copper. This is one I remember particularly well. And this was bronze. And we were doing some experiment that would turn copper into bronze. And John would plot them for us, and only instead of little dots, he would have big dots with circles around them. Do you remember this? and they would sort of form a line, and our job was to find the best line that went through the points. Remember that? And sometimes we would draw our own line, sometimes we'd have to use John's lines. Well, this is how scientists use the equation of a line, y equals mx plus b. This is how scientists use the linear function, if you want to use the function word, the F word. They would use it to draw conclusions about their scientific experiments, right? Today we're going to talk about how business people use linear variation, all right? And the best way to do it is just to jump into a problem. Don't worry, it's not as annoying as these were. 62.3. Here we go. The total cost varied linearly with the number produced. Okay, let me just write that down. Total cost Okay, this gives us lots of good information. The total cost varied linearly with the number produced. That means the number produced, which we will call n, is what we call the independent variable. It's like x. The total cost, which we will call c, is the result, and that's logical, right? However much something costs is going to depend on how many of them you make. Imagining that we're the factory that makes Hot Wheels cars, right? The number of cars we make, if we make 1 million cars, the cost is going to go up. If we make 1 billion cars, the cost will go up even more. So they go together. Okay, that makes sense. So the cost is going to be the dependent variable, which is y. X is always the independent variable. We choose our x's. Y is always what staggers along behind it, right? We calculate it. And this makes sense, right? That you figure out how many Hot Wheels you want to make in your factory, and that will drive what the total cost is. So now what we've done is we've created a pattern where we know that one drives the other. Okay. When we go to graph this, we know it's going to look like this. This is going to be the n axis, and this is going to be the c axis. Okay. Let's look at what else they tell us. John, when 100 were produced, the cost was $700. We can write that as a pair of points. 100 was the number produced. 700 was the cost. So we see our little X and Y thing is working, right? 100 were produced. That led to $700 as cost. And now John gives us another point. When 400 were produced, the cost was $2,200. All right? Write an equation that gives cost as a function of the number produced. Now, I want to write that down because I don't want that to scare you. And there it is, produced. There it is again. It's that F word. And if someone's listening in on this, the F word is function. It's not the other F word. Okay, whenever we see this word, it throws panic into students, but I want to change that energy. Cost as a function of the number produced, that just means cost is the dependent variable and the number produced is the independent, all right? Cost is driven by, cost is related to, cost is calculated from. There's lots of different ways to say that without using the word function, but function is the mathy way to say it. But it's just a calculation. You know how to do that. Cost is calculated from the number produced. All right? So I want you to get into the headspace where this word function makes you feel comfortable. There's a mapping. You can almost always, you have to change the tenses of the word a little bit. If you remember that a function is a mapping between two things, cost is a mapping between the number produced. That doesn't flow right from a grammar point of view, but the idea is that for any number produced, there will be a cost that connects to it. All right, so let me just draw in the picture. We don't need a graph to solve this problem, but I just want you to see roughly what we're looking at here. And I'm gonna put in some numbers to help us graph this. One of the weird things that students take a little while to get used to is that in these graphs, just like in the science ones, the grids, the scales are often quite different, and that's okay. We can do that. All right, our first point is 100, 700, so that's gonna be about like there. And then our second point is 400, 2,200, and that's gonna be about there. So what we're saying is that to run this factory that makes Hot Wheels, the number of Hot Wheels we choose to produce is going to drive up the total cost of the production run. Does that make sense? So we have to figure out how many we want to produce, and then we have to deal with how much that's going to cost, and then that would be useful for helping us like set the price, or maybe decide, oh, we need to make even more, or that's too expensive, we need to make less, right? Business people could use this information to decide how to run their factory. So it's super useful. And did I say this? I was an accounting major in college, and I had a whole class where we just did this kind of thing. It was super fun. I thought it was fun. So now we can stop thinking about this whole Hot Wheels factory cost function thing, and we can just manage the numbers. How do we find the equation of this line? Oh, we use slope formula, and then we'll use one of those points to solve for B. We've done that a billion times. It's the very same thing. So I'm going to copy my points over. John gave us these. We didn't do anything to figure them out. And we say, okay, this will be X1, this will be Y1, this will be X2, this will be Y2. Remember, it doesn't matter which one we call the ones or the twos. It'll work out. So the first thing we're going to do is we're going to find the slope. And to do that, we're going to use the slope formula, which looks like this. You're probably going, oh, yeah, I kind of remember that. Make sure you have this written in your notes and make sure that you keep it memorized. Keep it in the top of your brain. Okay, I'm going to do some buckets. Even though I don't have any minus signs here, I just don't need to confuse things. All right, we start with Y2. We subtract Y1, X2, X1. Beautiful. What we get then is, and that means that 5 equals m. Oh, that's a nice easy slope, isn't it? All right. And I'm going to resist the urge to get into a bunch of accounting explanations of what this all means. That's not a 1. I was going to put a box around it, and then I realized no. Second one is we find B, right? It's our old friend. So M is the slope and B is the y-intercept. You remember that? This is what we're trying to build, right, for that line. We're quote unquote modeling. We're modeling a function. Those are fancy words that describe what we're doing. We're just using this old tired formula to find the equation of the line, but we have all these fancy ways of saying it. And I don't want you to be psyched out by those other words. Okay, so to find B, what we do is we use our M, and then we use either pair of x and y, plug into that. I'm going to use the easy pair. So I'm going to write 700, well, I mean they're easier because they're smaller, equals 5 times 100 plus b. Make sense? I'm just plugging in the y, the m, and the x. This is 500. So I'm going to subtract 500 from both sides. Oh, I didn't need that line there, sorry. And we get, that's gone, we get 200 equals b. Beautiful. So now we know, I'm going to go back to my picture. The equation of our line right here is y equals, I'm going to write it here first, just a second. We know y equals 5x plus 200. But just like when we do this in science, we're going to change out the x and the y to make it cute, right? To make it look like this. So we're going to write C, the cost equals 5 times the number produced plus 200. That is the equation of this line. That is cost as a function of the number produced. That shows how the total cost varies linearly. All right, so all these fancy words can be used just to describe the equation of the line. This is a model of the cost projections at our Hot Wheels factory. It's all kinds of fancy things, but you and I know it most familiarly as the equation of the line. Cool, right? So this is how it's used in business. This is how it's used for science. I am really glad we don't have those stupid dots, aren't you? Okay, and there's one more of these problems, and then we are done with lesson 62. Are you ready? Wait. No, there is not. We're done. I thought there was another one of these problems, but there isn't. That was 62-3. Yeah, we did two of the abstracts and one of these, and that's all there is. We're done. I'm sorry. I wanted to do one more problem. I'm sure you're just as disappointed as I am. Okay, linear variation in a business model. The end. Goodbye.